Good evening, audience. This afternoon, we're going to be looking at the linear algebra project and really focusing on linear algebra behind spectral clustering. I'm TJ Bryan.
I'm Rico Shu.
I'm Anirudh Ramprasad.
I'm Bryan Good.
And this is our final project for Math 214. So before we really jump in, we're going to go over the agenda of what we're really going to be covering throughout this presentation. First and foremost, we're going to go through an introduction to what spectral data clustering actually is. And we're going to follow that up right after with clustering algorithms and really how we came up with all of the data. Thirdly, we're going to go through the methods and the findings and really the process of how we broke this whole project down. We're going to follow that up by how this linear algebra applies to this practical project, as well as the takeaways that we got and really how are we going to apply this into when we go into our professional careers. Then we'd like to really show you the code that we put together and that hopefully that'll help you to visualize how we were able to get our results. And then we're going to finally go through our conclusion. So what is spectral clustering? So spectral clustering is a method in which we assign data to groups where data is with other groups in similarities. And from these data in different groups, spectral clustering allows us to find similarities between these different differences in regards to the relationship between data points. And so for a more theoretical overview, spectral clustering makes use of eigenvalues of the similarity matrix of coordinates to perform dimensionality reduction before making use of other clustering techniques. And we're really going to explain this as we go through the rest of the sections. So for our data set, we found a data set of over 17,000 FIFA 2022 player statistics on Kaggle.com. And for each player, it's actually given over 60 attributes. So we had a lot of data to work with. And although with MATLAB, we were limited to only 500 players, and we only used 7 attributes for each player, the ones that the group decided to be most important in determining a player's position. And so with that, I'm going to hand it over to Ani to really go through the clustering algorithm.
Hey audience, I'm Ani, and I will be going through the NJW clustering algorithm that we use to help cluster all of these different football players based on their respective positions. So let me just take you through a brief overview of the algorithm. In the first step, we start by creating a similarity matrix W between all the different players, right? And this is done by the formula shown on the slide over here. So the similarity between player I and player J is given by this complex formula, and the similarity between the player and itself is given by 0. After this, we compute the diagonal matrix of this similarity matrix, which is done by summing all of the similarities for each of the players. We then use this diagonal matrix to normalize W, the similarity matrix. The main purpose of this is to ensure that all of the similarity values are between 0 and 1. And what this basically does is it makes sure that whatever clustering we do afterwards is far more accurate. Moving onwards, here's where the real bulk of the linear algebra comes in. Here we perform dimensionality reduction on the normalized similarity matrix. What we do here is we basically calculate the k largest eigenvectors of the normalized similarity matrix and concatenate them together to form an eigenvectors matrix. Now, I know that kind of sounds complicated, right? But the main purpose behind this is to sort of reduce the dimensions on which our data is being clustered on. And this is extremely helpful in clustering the data as it makes our results far more accurate. You can think about it this way, right? Instead of measuring what to cluster our data on based on like 500 characteristics, we're instead only going to use 3 here. After we perform this dimensionality reduction, where we basically reduce the number of dimensions we characterize our data on, we use k-means clustering to cluster our data into k clusters. Now I will head the mic over to Rico to talk about what specifically we did, to explain our MATLAB code and to explain our findings. So Rico, over to you.
Okay. Hi audience, I'm Rico. I will then present to you how we apply the algorithm in MATLAB. So this slide is an overview of our process. It contains 8 steps that read the data file, format the desired data set, manipulate the data, and visualize the data using scatter plots. In step 3, we calculate our similarity matrix with a nested for loops to go through each row and each column using the formula shown on the top right corner. This step is a bit time consuming. However, we do this to save time for the k-means clustering algorithm in later parts, since we only need to deal with a significantly smaller matrix in the later part. Moving on, in step 4, we calculate our diagonal matrix that will be used to normalize the similarity matrix using a single for loop, since we only care about the diagonal entries of the matrix, and we will leave all other entries 0. The modified matrix will then be used for k-means clustering, with each row representing a different player, with a total of 500 rows. Note that now we only have to deal with 3 entries each row instead of step 7, which were the attributes that we picked for the players. This saves time for k-means clustering algorithm. So now it is worth noting that sigma, which is a term used to scale the similarity matrix, plays a very important role in the accuracy of our algorithm. We first picked sigma equals 100 and obtained the following similarity matrix. Note that the difference between entries are not that significant. So this leads to a 74.6% accuracy, which is not ideal. But we are then able to improve accuracy by picking an alternative sigma value. We then chose sigma equals 10 to scale the similarity matrix in a different way. We then obtain a similarity matrix with more significant differences between different entries. And as a result, we have achieved 92.6% accuracy with the exact same algorithm. I will then hand over to Ani to explain how linear algebra is applied in our algorithm.
Thanks, Rico. So how does linear algebra apply to our project? Well, linear algebra is the base backbone of how the NJW spectral clustering algorithm works. This can be broken down into 2 parts as shown in the slide here. For the first part, it can be noted that the algorithm makes extensive use of matrix manipulation. This can be noted through the formation of the diagonal matrix D, the normalized similarity matrix W tilde, the base similarity matrix W, the eigenvector matrix U, and the normalized eigenvector matrix U tilde 2. Without linear algebra, none of this would be possible. The second area of interest in how linear algebra applies here is through the dimensionality reduction shown in reducing the characteristics in which the data is being measured on. If you remember, this algorithm computes the eigenvectors of W tilde to form the eigenvector matrix U. This thus saves a ton of time in the actual k-means clustering algorithm and ensures that the result is more accurate than would be if we were measuring on a lot more data than we currently are. Now I will hand it over to Bryan to talk about some key takeaways our group has learned from this project and to conclude us off.
Thanks, Ani. So throughout the span of working on the project, we learned many different things. First off, we discovered a couple different ways that what we've been learning in class can apply to many different situations in the real world. One being an advanced machine learning algorithm, such as the one that we calculated and created. We also discovered the numerous fields that linear algebra can apply to other than pure mathematics, such as computer science. And we learned how to analyze a problem and work as a team to solve it. Next, I'll show where you can find our code. We uploaded to this Google Drive link, so if you would like to view our code, go to that link. And finally, for our conclusion, spectral clustering using the NJW algorithm is a way for us to cluster data into different groups using many ideas rooted in linear algebra. In our code referenced on the previous slide, we implemented this algorithm through MATLAB using a data set of FIFA 22 player attributes. And in our example, we clustered players into 3 different position groups. But the same principles can be applied to many large data sets in order to cluster data into a chosen number of clusters in many situations.
Thank you for paying attention to our presentation.
And this concludes our presentation.